my name is Nick Moore, and this is my research presentation for Game Engine 3. I'll be talking about soft body deformation through the use of spring mass and pressurized body models. So your first question might be, what are soft bodies? So soft bodies are 3D models where the relative distance between the vertices is not fixed. And this is in contrast to rigid bodies, where those distances are fixed. So all the models we've used so far in the Game Engine series have been rigid bodies. So if you think about the space frigate, if you pick two vertices on it and look at the distance between them, that distance is not going to change relative to the distance to another vertex. So obviously we can scale the size of it, but all of those distances are going to change by the same scale. Whereas with soft bodies, you can change the distance between any two vertices without affecting the other distances. And so that's how we're able to recreate, say, the cloth being blown upward or the hair on the dancing man. And so we use simulations based on physical models to determine how these distances should change. And so the goal of these simulations is to mimic real-world visual effects, not actually mimic the physics. And so the reasoning there is, by focusing on just the visual effects, especially for games and movies, we can use models that are significantly cheaper in computation to recreate the effects. All right, so now that you know what a soft body is, why should you care about them in respect to game development? So I have three examples here. The first is model deformation. And if you look at the cars crashing into the wall in the bottom left, the top car collides and instantly changes its model to the crushed car, whereas the bottom car squishes and compacts as it collides with the wall. So the bottom model could be recreated with soft bodies in conjunction with rigid bodies, whereas the top model is just swapping between two rigid bodies. So the use of the soft bodies allows us for a realistic car crash. The second would be cloth or hair, like we saw in the previous slide, and also in the bottom right with the mannequin doing the cartwheel. So by using a soft body simulation on the overcoat, the programmers were able to accurately recreate how it might behave. The final example is with biological objects or tissues. So you can see that as the cheetah walks, muscles stretch and compress, giving an accurate visual effect of what the muscles of a big cat might look like when it's walking. And this can be done using soft bodies. To implement soft body deformation in our game engine, I decided to use two different models. First, the spring mass model, and second, the pressurized body model. So the spring mass model uses a collection of springs and masses to simulate the internal forces on a three-dimensional object. So if you look at the cube on the left, you'll see the 8 vertices in the corner and then a bunch of black lines. So each black line is a spring that connects a vertex to another vertex. So for every vertex, there is a spring to every other vertex. So if you have a model with a significant number of vertices, you'll end up with a ton of springs. So the springs are governed by the equation on the right, where F is force, K is your spring constant, which is a measure of essentially the tightness of a spring. X is your displacement distance, which is the difference between its current length and its rest length. So the natural position of the spring. D is a dampening constant, which is a value that is used to reduce harmonic oscillation over time. And V is the difference in velocity of the 2 point masses, which are the vertices. So this formula is based on Hooke's law. And how this works in implementation is the springs are iterated over and the force of each spring is calculated and then applied to the two vertices at each end. So one gets a positive force and the other gets a negative force. Once all of those have been looped through and applied to the vertices then use the force to calculate the acceleration and velocity on that point, and in turn, its final position. So how much it moves based on that force. The first thing I implemented with the spring mass model was a rope. So I wanted to implement something as simple as possible, which in this case is a series of masses connected by springs. So each green dot is a mass, and the invisible area between each green dot is a spring. And so how this works is there is a force of gravity applied to each mass, and that force, in conjunction with the force from the springs, is used to move the masses. So when it's initially let go, the force of gravity brings it down, and then as the masses start to pull on one another, that force from the spring will stretch or compress and cause it to behave like you would expect a rope to. So once I got this working, I wanted to move to a slightly more complex model, which in this case is a cube. So here I have my spring mass cube, and like I talked about previously, there is a spring connecting a vertex to every other vertex. So every vertex has 7 springs attached to it. And so again, this is being acted upon by the force of gravity and the force from the springs. So as you can see, when the cube collides with the ground, it compresses and then bounces up. And that's due to the spring. Um, so when it hits the ground, the springs compress and the force increases, and then as they expand, it launches it vertically off the ground until it hits a resting point. And so I have input to add upward force to create this bouncing. So like right here, that's input force by me. All right, and so I was able to get this model working, but it took some additional effort on my part to get the model data ready for the spring mass model. And I'm actually going to talk about that later because I have some visual representations of that. All right, so once I got the cube working, I wanted to try this with a sphere. So my goal was to recreate how a sphere would look when it hits the ground. So as you can see, when this sphere hits the ground, it compresses a little bit and then bounces up some. But so we're going to get a more energetic fall coming up. So when the spring collides with the ground, it compresses, but not really in the way you would expect a sphere to compress. And it kind of seems like we're losing volume with this method. So we're still getting some bouncing thanks to the internal force of the springs, but we're not really getting that spilling over that you would expect from a sphere. So while the spring mass model works well for a cube, it might not be the best implementation for a sphere. So the behavior of the sphere really pushed me to explore an additional model, the pressurized body model. So the pressurized body model is an expansion on the spring mass model. With this model, spring masses are still used, but the springs only cover the surface of the object. The internal forces are governed by a pressurized body. And so this is calculated using a derivation of the ideal gas law. So the equation you see on the right of the screen is the governing equation for the internal force. So we're still using springs, so the previous equation still applies, but only to the surface of the object. Here, with this equation, we have F is our force, S is our surface area of our 3D object, N is the number of moles of gas, R is our ideal gas constant, and T is our temperature, and V is the volume of the three-dimensional object. So for practical purposes in our game engine, N, R, and T are fused into a singular constant C. So this equation can really be thought of as F equals SC over V. And so calculating the surface area and the volume is very important for this implementation. And so to do that, to calculate the surface area, what I did was I calculated the area of each triangle on the rendering frame of the model and summed those for the total surface area. To calculate the volume, I used a process called tetrahedralization. And so this process is very similar to triangularization, except it's for three-dimensional objects. So triangularization is the process of taking a 2D plane and breaking it down into triangles. This is the same thing, but for a 3D object and breaking it down into tetrahedrons. So breaking it down into tetrahedrons, I can then calculate the volume of each tetrahedron and sum them for the total volume of the system. And so the purpose of using the pressurized body model over the spring mass model is this internal force hopefully will create a more realistic object behavior. My first implementation for this model was going back to the cube. So I have my pressurized cube here. And so there's a spring on all of the wireframes you can see, and an additional spring essentially crossing the X on each face. And so as you can see with a pressurized model, the cube behaves a lot more squishy. And so when it collides with the ground, it compresses more, and actually when it reaches its resting state, it doesn't really form a cube anymore because its height is less than its width and depth. And so we can already see that with this model, our objects are behaving less like a bouncy ball or bouncy cube and more like a compressible object. And so the next thing I did was back to my sphere. As you can see, as the sphere rotates, it doesn't really look like a sphere and is more of a hot dog shape. And so this came from how the internal pressures are calculated on the vertices. And so those vertices all have an equal internal pressure applied to them that is applied in the direction of the normal force. And since that internal pressure is applied equally across all the vertices, when you have areas with a higher concentration of vertices, those experience a greater internal force. Hence why the poles where there are more points are experiencing a greater push away from the center. But we can already see that this implementation is working better than our spring mass sphere in regards to a sphere being pushed against the ground. So you can kind of see that overflow. Instead of just the mass going away, it's pushed out to the sides. And so one important thing I learned when implementing the sphere, in addition to the internal pressure issue, is that your models have to be made with intention for this. So when I initially was just trying to use my calculated sphere model, I ended up with additional points at the poles and along one seam of the sphere. And so that internal pressure actually just caused the sphere to unfurl. So I had to correct for this by finding identical points on the model and making sure that I was using the same points for the springs. Whereas if this was unaccounted for along the poles, where you see I have 6 triangles meeting, I would have 6 points there that were not that were connected to individual other vertices, but not behaving as one. So to use this model, there's extra work that needs to be done to the 3D model before it can be properly implemented. So with my learnings about the internal force, I applied that for this sphere. And so what I did was, instead of just blanketly applying the same internal force, I applied the internal force based on the surface area of the triangles the vertex touches. So the greater surface area of the triangles that are connected to said vertex, the greater force that will be applied. And so you can see right off the bat, we have a more spherical shape and less like a hot dog. One issue with this, though, is it does behave a little more, I would describe, wonkily when it collides, but having the actual shape we intended for is more important than that bit of wonkiness on the deformation when it collides with the ground. So I was able to achieve both of the goals I set out, implementing the spring mass model and pressurized body model in our game engine. So if I were to continue this project, some next steps I would have would be a more robust collision detection system. So the way it's currently set up, the soft bodies just collide with a planar surface. But if I could have a soft body collide with a rigid object, say a soft body sphere, colliding with the edge of a rectangle, rigid body, and rolling across the top, that would provide a lot more visually interesting simulations and a lot more accurate to what you would see in a game. The pressurized model could work well with imported models. There's just a lot of corrective work that would need to be done to get those models in the right state. And also compute shaders for the physics calculations. So the physics calculations can all be parallelized because they are all summed and then applied to the vertices. So using a compute shader for that would really help with performance. Here are my sources for my images. Thanks for watching my video.